So welcome to our lecture video in fluid mechanics under the topic total hydrostatic force on plane surfaces. So in this video we will solve the sample problems, the 5 sample problems in the module. But before that, let's have a short discussion on this topic. So we have here the total pressure on plane surfaces. In the total hydrostatic pressure on any plane surface is equal to the product of the area of the surface and the unit pressure at its center of gravity. So take for example, if we submerge a body, so here we have here a submerged body with irregular shape. So we will have to first take the pressure, or the force is equal to the pressure. So the pressure here is gamma of the liquid to where the body is being submerged, and the HC, or that is the vertical distance from the liquid surface to the submerged center of gravity of plane area. So it mentions there center of gravity. Therefore, we are focused on this portion here. That is the center of gravity, HC. So in this figure, it is bar H bar, or in the formula we will use HC. Okay. And we need also to consider that the area to be solved here is the area, the surface area of the submerged body. So we need to solve for the area. For in this figure, we have an irregular shape, but in our examples, if we submerge regular shapes, then it is easier to get the area of the plane surface. So the formula for the force here, the hydrostatic force, is equal to the, again, that is the gamma of the liquid surface to where you submerge the liquid, the body, multiplied with the vertical distance from the liquid surface, and that is the HC, and the area of the submerged surface area of the plane. Okay. Now, how about the center of pressure? How do we get the center of pressure? So where is the center of pressure here? In the body, in the submerged body, the center of pressure is usually found below the center of gravity. So the center of gravity is where you balance the body or any object above the water surface. So when we balance a certain object in the atmosphere, we balance it in its center of gravity. But when you submerge that certain body, the same object, if you submerge it, the center of gravity shifts to its center of pressure. So it goes to the center of pressure because the pressure, when it is being submerged, you increase the pressure as you go deeper. That's why the center of pressure of any body goes down, it goes lower than the center of gravity. Therefore, we will need to solve for the center of pressure. How do we solve for the center of pressure? We need to find the value of eccentricity E. So what is eccentricity E? The eccentricity E is the perpendicular distance between the horizontal axis through center of gravity and the center of pressure lying in plane of area. So it is the distance between the center of gravity and the center of pressure. So here is the formula to be used in solving for the eccentricity E. So E is equal to Ig, or that is the moment of inertia of area with respect to the horizontal axis through its center of gravity lying on its plane. And then that is divided by SS, or that is the statical moment of area with respect to the line in which the area extended cuts the surface of the liquid. Now here is the formula for the SS. So S sub S is equal to the area of the surface of the body being submerged. So the area multiplied with the YC, where YC is the inclined distance from the liquid surface to the submerged center of gravity of the plane area. Now YC is the inclined distance of the center of gravity to the liquid surface. Now this is YC in our figure. The Y bar here is actually the YC if we are concerned with the inclined bodies. But if the inclined if the body, the submerged body is being positioned vertically, then there's no need to solve for YC. Rather, we will just stick with the HC. Okay, so that's the difference. You can get two different values for eccentricity E depending on the position of the submerged body. So again, it depends on the SS. Okay? Because if we are dealing with a vertically submerged body, we will use here HC. If we are dealing with vertically submerged body. But when we are dealing with inclined submerged body, therefore, we will use here YC. So that's the two primary difference in using this formula. Now let's solve the examples. So we have 5 examples for this video, but we will cut it into part 1 and 2. So we will solve in this part 1, we will solve the examples number 1, 2, and 3. Okay, so we have here example number 1. We have a vertical rectangular gate 2 meters wide and 5 meters high. It is hinged at the top. So as you can see from the figure, the hinge here is located at point A. And this gate holds oil on one side. So the oil here is given the specific gravity of 0.84. So it's standing on one side at 7 meters deep. So it is 7 meters deep here. We need to compute for letter A, the hydrostatic force acting on the gate, and B, the horizontal force applied at the bottom required to open it. So how do we determine what is being asked here? It says there in letter A, the hydrostatic force acting on the gate. So where does we draw that hydrostatic force? It's located here. So the liquid is standing on one side. In our figure, it is located at the left side. Therefore, the force acting on the gate, this gate AB here, is at this position. So it is pushing the gate from left to right. Okay? So that is our hydrostatic force F. Now, where is the hydrostatic force located? It's located at the center of pressure, not the center of gravity. As mentioned a while ago, center of gravity is the location of the neutral or the where you balance the object when it is above the liquid surface. But when the object is being submerged, therefore, the center of the object shifts from the center of gravity and it moves towards the center of pressure. Therefore, our hydrostatic force is located at the center of pressure. So how do we solve for this? What's the formula? So the formula for the hydrostatic force is equal to the gamma of the liquid to where your object is being submerged multiplied with the HC, or the distance from the surface of the liquid up to the center of gravity, then multiplied with the area, the surface area of the object being submerged. Okay, so what is the unit weight of the liquid? Our liquid here is oil, and that is 0.84 multiplied with the standard unit weight of water, which is 9.81. That is in kilonewton per cubic meter. And how about HC? Now, HC is located from the surface up to the center of gravity. So this is your HC. So our HC now here is 2 meters. So of course that is the 2 meter height here. So 2 meters plus the 5 meter high gate. So in the problem it was mentioned that this gate is 5 meter high. So that is 5 meters divided by 2 to find the center of gravity. Then multiplied with the area. What's the area of the gate? So it's mentioned there that the area of the gate is 2 by 5. Okay. So this is the figure that you will see when your eyesight is at this side. Okay, if this is your eyesight, this is what you will see the gate. So 2 meters wide, 5 meters high. So that's the area, 2 by 5. So what's the answer here? 0.84 times 9.81 times 2 plus 2.5, then times 2 times 5. That is 370.82. 370.82, and the unit here is kilonewton because we're dealing with force. So that's for letter A, hydrostatic force acting on the gate. How about letter B? It's asking for the horizontal force applied at the bottom required to open it. So, to open, what do you mean by the force required to open? So, to close the gate, in order to know what force to open, you need to know what force to close. So, here we have a force, hydrostatic force from the oil acting on the gate. It's pushing from left to right. So to close the gate, you need a certain force here that is opposite. So that is opposite from the hydrostatic force. So this is the force to close the gate, the force at B. Okay. Now in order to open it, it means that it will exceed the closing force. Okay, so in order to know the force required to open, you need to find the value of F sub B. So how do we find the value of F sub B? We need to compute for the summation of moment at A. So we need to have the summation of moment here at A. Now, in order to get in order to complete the summation of moment here, we need to find the value of E, this eccentricity E. That is the distance from the center of gravity to the center of pressure. So we have here summation of moment at A is equal to 0. So we have here the force at B So we put here sa positive clockwise. So force at B multiplied by the distance 5 meters, then minus the force or the hydrostatic force there, and that distance here is 2.5 plus E, the eccentricity E. Because 2.5 here is distance from A to the center of gravity. That is equal to 0. So we need to find the value of E. So for the value of E, we have here the formula E is equal to moment of inertia over A H sub C. So what is the moment of inertia of a rectangle? The moment of inertia of a rectangle is base times height raised to 3 divided by 12. So BH 3 over 12. Then we have the area HC. HC because we are dealing with vertically submerged object. Okay. So our base here is 2 multiplied with our height 5 raised to 3 divided by 12 all over 2 times 5 for the area. And as for the HC, that is, again, it is 2 plus 5 divided by 2. Okay, so what's the value for E? So that is 0.46. 0.46 meter. Substitute the value here in our equation. We have here FB times 5 minus the force 370.82, 2.5 plus 0.46 equals 0. So F sub B is now equal to 370.82 times 2.5 plus 0.46 divided by 5. So that is equal to 219.525 kilonewton. So this is the force B. Okay, so this is the force B here. That is that's stopping it from being opened. Now this same force, if you exceed this force here, you can open now the gate. So that's example number 1. Let's go to example number 2. We have a semicircular gate AB with a radius of 5 meters. So we have here the radius 5 meters. It is hinged at B. So here is the hinge. Determine the hydrostatic force acting on the gate, and B, location of the hydrostatic force from B. So where is the liquid located? In the figure, you can locate the liquid at the left side. Therefore, our hydrostatic force is here, F, at the center of pressure. So what's the F here? For letter A, we have the formula force is equal to gamma HCA. Now the question here is, what is HC? So we know that HC is located from, okay, HC is located from the center of gravity up to the surface of the liquid, right? So where is the center of gravity for semicircle? So it's located here. So this is the center of gravity, or the centroid. So what is the formula for the center of gravity for a semicircle? So it is, from the diameter, it is 4r over 3 pi. So it is 4r over 3 pi. So we will now compute here HC. So we will put here HC is equal to 9 minus 4r over 3 pi. That is equal to 9 minus 4 times the radius here is 5 meters divided by 3 pi. That is equal to 6.88 meters. So now we have here gamma of what's the liquid here? What's the so if it is not mentioned, then therefore our liquid here is water. Okay, so we'll put here water surface. So we have here a liquid that is water, 9.81 gamma. Our HC is 6.88, and the area of a semicircle is 1/2 of pi radius squared. So 9.81 times 6.88 times 0.5 times pi times 5 squared. That times pi. That is 2650.44 kilonewton. Now let's go to letter B, location of the hydrostatic force from B. So our hydrostatic force here, F, location from the bottom. So our hydrostatic force is at center of pressure. So how do we solve for the location Y? How do we solve for that? Now we will need to find the value for E, right? Because our E here, our center, our eccentricity E is located, or is the distance from the center of gravity to the center of pressure. So Y here is equal to 5 divided by 2. Of course, this locates the center of gravity, minus the E, the eccentricity E. No, it's not 5 over 2. Sorry, it's not 5 over 2. Remember, we're dealing with a semicircle. So it's 4r over 3 pi minus E. Okay, so that's the right formula there. So we'll now solve for the value of E. So E here is Ig over AHC. We're dealing with a vertically submerged object, so we're using HC. Now, what is the moment of inertia of a semicircle? That is 0.11 r to the 4th all over AHC. Then we have here 0.11 raised to 5 times 5 raised to 4 divided by 1/2 pi r squared, and then our HC a while ago, which is 6.88. So what's now the value for E? 0.11 times 5 raised to 4, 1/2 shift pi times 25 times 6.88. So that is 0.25 meter. Okay, finally we now have our Y. Y here is equal to 4 times 5 all over 3 pi minus 0.25. So Y is now equal to 20 divided by 3 pi minus 0.25. 1.87 meter. So 1.87 meter is the distance from point B, or from the bottom, up to the center of pressure. So that's example number 2. Okay, so last for this video, we have example number 3. Example number 3, we have rectangular gate, 1.2 meter wide. It rests against a smooth wall at A. So take note, there's no given figure, so you need to imagine how it is being positioned, how the rectangular gate is being positioned here. So this rectangular gate is hinged at B, located at 5.2 meters below the water surface. A, or point A, is 2.92 meters to the right of B and 2.2 meters above B. Compute for the force acting on the gate and the horizontal force exerted by the wall at point A. So how do we visualize this? So there is a rectangular gate given width of 1.2 meter, and there is a smooth wall at A, hinge at B, and the question here is, where do you locate B? So in the problem, it's described as 5.2 meters below the water surface. So it says there your point B. So if this is your water surface, your point B is located 5 meter below the water surface. So 5.2. And then, so let's put there B. And then point A is 2.92 meters to the right of B. So here you go. This is your point A. To the right, that is 2.92 meters. And then it's 2.2 meters above B. So 2.92 to the right of B, and then going upward 2.2 meters. So that is here. It's located here. So this is your 2.2 meters, and this is point A. Therefore, you can conclude that the gate being described here in number 3 example is actually inclined, and it is resting on a smooth wall at A. So here is our point A, which is actually the wall that is being mentioned here in the problem. So this is your wall. So that's the representation, or this is the figure for number 3. So we have it here. So here is our figure. So from this figure, we are being asked what is the force acting on the gate. Now the question here is, how do you position the force here? Is it horizontal, vertical, or is it inclined? So what's the rule here when it comes to submerged bodies? So when you submerge any object, when you submerge any body here, the force acting on the surface of the object is always perpendicular. Okay, so the force acting on the object is always perpendicular. Therefore, the force here is acting perpendicular. So this is our hydrostatic force, F. So it is 90 degrees with the gate, the inclined gate. And the location of this force is the center of pressure. Okay? So what's being asked? The force. Okay, we need to solve first for the force of. So the formula for the force here, letter A, is equal to gamma HC area. And we're talking about the area of the inclined gate. And to get the area of the inclined gate, we need to find the length. So we were given here in the problem the width of the gate, but there's no mention of the length of the gate. So we will solve it. So this is the gate that is being mentioned. Okay, so we need to find here the length, and that is by Pythagorean. Okay, so that is square root of 2. So the square root of 2.92 squared plus 2.2 squared. The answer there is square root of 2.92 squared plus 2.2 squared. This is equal to 3.65 or 3.66 meters. So this is 3.66 meters, and we have here the 1.2 meter width. Okay, and the center of gravity is located here, CG. Now we need the value for HC. How do we get the HC here? Here is our HC from the center of gravity to the surface of the, what's this? Surface of the water. Okay, so this is water. So this is HC. Now as you can observe here, our HC is equal to 3 plus 2.2 divided by 2. Right? And that is equal to 3 plus 1.1. That is 4.1 meter. So we now have here our force is equal to 9.81 unit weight of water times HC 4.1 times the area, which is 1.2 times 3.66. So that is now our force. That is equal to 176.65 kilonewton. Okay, that's for letter A. Now let's go to letter B. Find the horizontal force exerted by the wall at point A. So in what direction is the force at point A? Now there is a force here from the water surface, from the water, and it's acting to the right. So we need force to go opposite it. So but then again, we are dealing with this wall here, therefore the force is to the left. So horizontal force at A. So we're looking for the horizontal force at A. Why horizontal force? Well, the wall here is mentioned as smooth wall. So when we are dealing with smooth walls, so there we remove the friction here. Friction, therefore there is no upward force. So there is no upward force here to act as a resisting force due to friction. Therefore, since it is a smooth wall, we are dealing with horizontal force. Okay. So how do we find the value of FA now? To find the value of FA, we are to, so for letter B, so we will have a summation of forces at B. Summation of moment, I should say, a summation of moment, sorry, at B is equal to 0. We'll have it positive counterclockwise. Okay, so that is FA, so FA times 2.2 minus, we have here F multiplied with, let's name this as Y. From the bottom here up to the center of pressure, let's name that as Y. Okay, force times Y is equal to 0. Now how do we get here the value for Y? Again, we will need to solve for the eccentricity E. There, the eccentricity here. So Y is equal to the 3.66 divided by 2 for the center of gravity minus the value of E. Now what's the formula for E? E is I sub G all over A, and we are dealing with inclined surface, therefore we have to use YC. Okay, so this is equal to the base times height raised to 3 divided by 12 all over A YC. Now how do we get the value for YC? So YC is located here. Oops. So this is your YC from the center of gravity up to here. So this is YC. Now how do we get the value for YC? So this is HC, and it forms a triangle. If you notice, there is a triangle being formed. So first we will need to get the value of this angle. The angle here. What's the value of theta here? The value of that theta is equal to the value of this theta here at this incline of the gate. Therefore, to get the value of theta, we have here tangent theta is equal to the 2.2. So this triangle here. So let's draw first the triangle where we're getting the theta. We're using the triangle 2.2 here and 2.92. So tangent theta is equal to 2.2 over 2.92. So theta now is equal to inverse tangent of 2.2 divided by 2.92. That is equal to 0. Oh, sorry, I was in radian mode. Sorry. So inverse tangent of 2.2, 2.92. So 36.995, or let's just say that is 37. 37 degrees. Now let's solve for the YC, and we're dealing with this kind of triangle for that. So that's our HC and YC. So this is the HC, this is the YC, and this is the theta. Okay, so we have here tangent of theta is equal to the HC all over the YC. Now, a while ago, we were able to get the value for HC. Our HC here is 4.1. So that is our HC. So tangent 37 is equal to 4.1 over YC. Therefore, YC is now equal to 5.44. Oh, it's not tangent, so I'm sorry. It should be, sorry, it's not tangent. It should be sine. Sine. 4.1 divided by sine 37. So 6.81. YC is 6.81 or 6.81 meters. So we can now use it here in our calculation for E. Base of the gate is 1.2. And then the height of the gate is 3.66 raised to 3 divided by 12. And then we have the area of the gate, rectangular area, that is 1.2 times 3.66 multiplied with YC 6.81. So what's now the value of E? 0.164. So 0.164 meter. Then let's go back to the value of Y. So here, we're now going to find the value of Y. Y is now equal to 3.66 divided by 2 minus 0.164, and that is equal to 1.67. Or 166. Okay. A. So 1.67 meters. And then we will now use the value of y in this equation. So FA times 2.2 minus the force that we were able to solve, 176.65 times the value of y, 1.67 equals to 0. So we now have here force A, so 176.65 times 1.67 all over 2.2. 134. So that is 134.09 kilonewton. So that's the force acting, or that is the force exerted by the wall at point A. So this is our example number 3.